All right. Often you hear people say, I'm not good at math. Anyone here? Raise your hand if you ever thought or said out loud, you're not good at math. Yeah, a bunch of you. All right. I can tell you good news. There's no such thing as being bad at math, okay? So, but my students also say this all the time. And there's normally a follow-up. Is, who needs math? I mean, I've got the calculator on my phone, so most of us interact with mathematics every single day without even realizing it. And in fact, there's a lot that we can do with mathematics beyond the calculator on your phone. And today, hopefully, I'll show you an example of this. Now, since the time of COVID-19 pandemic, I should say the SARS-CoV-2 pandemic, mathematical modeling has come to the discussion, really. So some of you might have heard about mathematical modeling, maybe, or disease prediction, disease forecasting. Some of you might have heard about basic reproduction number, R0, or herd immunity. But what does it mean? Now, when I have to face a mathematical problem, I always remember the wise words of Master Yoda. Do or do not. There is no try. Okay? So when I have to explain to my family what I do for a living, developing mathematical models, I say, I'm like the weather person, but instead of predicting if it's going to rain or be sunny, I predict how diseases are likely to spread. There is a long history of mathematical models, actually. So there's nothing new. Well, some things are new. In the second half of the 1700s, Daniel Bernoulli developed the first, let's say, recognized mathematical model. And this was using life tables to look at the expected survival in children. And the idea was that you wanted to promote inoculation, the predecessor to vaccination against smallpox. And in the early 1800s, in the advent of the smallpox vaccine developed by Edward Jenner, Francisco Javier de Balmis and colleagues conducted the first multi-continent vaccination campaign, the Royal Philanthropic Vaccine Expedition against smallpox. So they left from La Coruña in Spain, they traveled all the way to the Americas, across the Pacific to the Philippines, vaccinating individuals everywhere. So as you can see, mathematics have been informing public health already for quite a few years, right? So how does this actually work? So let's build a simple model, all right? Now, I've got here a few buckets, all right? So we're going to build a model. Now, the model that you build will depend a little bit on the disease you're interested in. Now, let's assume a simple scenario, a disease that you can only get once in your lifetime. So if you're born susceptible, you get infected, and afterwards you become immune to it. Something like measles or rubella. So we can then group a population into these three categories. I've got individuals that never had the disease, so they are susceptible. I've got individuals that currently have the disease, and they're infected. And then individuals that already had the disease, they recovered, and they're now immune. Well, let's imagine we start with a fully susceptible population. And I've got one infected individual. Now, as time passes, this infected individual is going to infect others. So there are people going to this bucket, right? Now, the speed at which this happens depends on the disease that we're looking at, how contagious it is. Depends how many individuals I have infected, how many susceptibles I have among my whole population. The infected individuals will also recover, right? So they'll go over here. So I can be doing this quite a bit of time. I'm not going to bore you too much with it, but I can do it for quite a while. So then you will have new susceptibles become infected, recovering from it. So R0, the basic reproduction number, relates to this: how fast I'm going from here to here, how fast I'm going from here to here. Now, at some point, I will run out of infected individuals. This might happen after I've depleted all of my susceptibles, or it can happen before, like just in this example here. These are called compartmental models, because my population is split in compartments. So what about herd immunity? Well, herd immunity relates to the proportion of my population that is immune. So we're looking at this bucket here, right? Now, if I have one infected individual and I have a lot of immune population, it's going to be really hard to find susceptibles. Obviously, in this case, we've got a bunch of recovered individuals. They are immune because they had the disease in the past. What if we had a vaccine? Okay, if I have a vaccine, I am vaccinating a bunch of people. Suddenly, this one infected individual is going to struggle to find the few susceptibles that are left because most of the population is immune. Now, these models can be made more complex, they can be extended, and in a way, it all works with mathematical equations. But today, I want to talk specifically about neglected tropical diseases. Now, neglected tropical diseases are ancient diseases that have a huge impact in both chronic morbidity and mortality, affecting over 1 billion people with devastating human, social, economic impact. We generally call these populations the bottom billion because they're the most vulnerable and marginalized communities. And because the diseases are so severe and have these impacts, the cycle of poverty is maintained. Now, some of you might have heard about leprosy or river blindness or maybe sleeping sickness. And these are only 3 out of 20 neglected tropical diseases recognized by the World Health Organization. Now, luckily, we have interventions for these diseases. And in fact, some of them are actually targeted for elimination by the international community for 2030. So some diseases are vector-borne. That means that species like mosquitoes or flies transmit the disease. So I can put interventions in place against the vectors, and that will reduce transmission. For example, using bed nets. For many diseases, we also have drugs that we can use. And we actually have safe and effective drugs like ivermectin, albendazole, or praziquantel, which have been used extensively over the last decades. But there's still many challenges ahead. Who do we treat, and for how long? What about those populations that we're going to miss? Are they important? When do we stop our intervention, and how do we monitor that these diseases are not coming back? And these are only a few of all the questions we might have, which are really important, particularly in these resource-constrained settings, where we don't have a lot of funding to necessarily work, and we need to make our programs as effective as possible, as efficient as possible. And this is where mathematics shine, because we can take those very complex situations and we can translate them to mathematical equations. And then we can solve them analytically on a piece of paper, if you are brave enough. You can also run it on your computer, right? So you can solve them numerically. You run simulations on your computer, if you're not afraid of the error codes. Now, some of these models can be fairly abstract. Some of them might be statistical models. And some might be fairly detailed, like mechanistic models. And mechanistic models, what we mean by that is that they're trying to simulate the mechanisms of transmission. So we're capturing the transmission dynamics. Now, to develop one of these mechanistic models, we start by going back to the biology. So, for example, many of these neglected tropical diseases are parasitic diseases. Okay, well, let's start with the parasite life cycle, right? Who does it infect? Are there any intermediate hosts? Do we need to worry about some potential animal reservoir that might transmit the disease? We create a model and we try to reproduce the life cycle. So we start with the egg hatching, then they'll go through different larval stages, then the parasite will become adults, right? And we can do that, we can simulate that in very abstract ways, we can simulate that in very detailed ways. It depends how much data we have, the disease that we're looking at. And then we can start running the models. And we can put simulations to run, and we can see, okay, how does the disease spread? Who's getting infected first? How are the populations interacting with each other? We can then add interventions, right? We had a bunch of interventions. Okay, let's imagine we put an antiparasitic drug, right? So we offer a drug one time. What if we're doing this every year, once a year? What if we're doing it twice a year, right? Now, as you can see, the combinations are endless. So in practice, when we develop these models, we do so in close communication with many stakeholders. So for example, we'll talk to policymakers who will decide which interventions they want in their programs, or the communities where the interventions are actually taking place. Now, there's a quote that is repeated ad nauseam in modeling talks, and it's by statistician George Box. All models are wrong, but some are useful. And I think we should embrace this. We should be comfortable with being wrong while we're being useful. We know these models are approximations. We don't have a magic crystal ball to predict the future. But these models have proven time and time again that they're useful. So let's embrace that. For neglected tropical diseases, some of these models can benefit vulnerable communities by accelerating progress towards elimination, even eradication of disease. So, as you can see, mathematics are much more than a calculator on your phone. Thank you very much.